All right, then let's get started. The simplest integration that you can do is one where you recognize that the integrand is there's a question?
I'm sorry, sir, I have another question.
Yeah.
Sir, do we have that policy where if our grade at the end of the semester is better without the mid, then the mid isn't counted?
Yes, I think so. Yeah.
Okay,
Okay.
thank you.
So the easiest integration is where you recognize that the integrand is the derivative of some function that you know, or maybe it's off by a constant. Then you're okay. That can be done almost immediately. Another case is where you recognize that you can see that you have the differential or a constant times the differential of some function in the integrand, and then you can use substitution, right? You let u equal something, and right, you recognize that you have a function of u and that you have du in the integral. Okay. Another approach that we'll see in this session is called integration by parts. Okay, and basically what integration by parts is it's the use of the corresponding differentiation rule is the product rule. Okay, so we'll use the product rule to derive the formula for integration by parts, and then we'll see a few examples. Okay, so remind you of the product rule, and if I take the derivative of u times v, let's suppose that u and v are differentiable functions at the point of interest, then that's equal to uv prime plus u prime v. Okay, now if I manipulate this a little bit, so I rearrange it until I get that uv prime is equal to uv all prime minus vu prime. Now I do an integral. So I have integral uv prime dx is equal to integral uv prime dx minus integral vu prime dx. Now notice that v prime dx is dv. Notice that u prime dx is du. And notice that the integral of a derivative is the original function. So you'll have uv. Okay, so then what you get is that if you see something of the form integral u dv, then that's equal to uv minus integral v du. That is the integration by parts formula.
So could you please go to the previous slide?
Yeah.
Just for a second.
Yeah.
Okay, thank you, sir.
Okay. All right. So if you see u, some function of x, times the differential of another function, v, then that's equal to uv minus integral v du. Okay? Now, this formula is always true, but it may not necessarily help you if you don't you're making the choices for u and for dv here, right? So when you make those choices, you have to take some care, right? Okay, and we'll see some heuristics for what choices to make as we go through the examples. Okay, so first example. The integral of x sine of x dx. I want to evaluate that. Is this is the integrand, the function you see between the integral sign and dx, is that integrand something, does that look like the derivative of some function that you know? Okay, no, it doesn't. Can I make a substitution that will make this easier? Well, when you do a substitution, you want to see a function u in the problem, and you want to in the integral, and you want to see a du. Okay? So, you know, letting u equal sine of x when you don't have a cos of x dx in the problem will not help you. Okay? So, the next thing to try is integration by parts, which is what we will do. I'm going to make this choice. I'm going to let u equal x, and I'm going to let dv equal sine of x dx. Okay? And then I is equal to integral u dv. So I let u equal x, you know, some part of the, some function, and then I'm going to let dv be sine of x dx. So that's the rest of the integral. Okay? So whatever you pick as u, whatever's left over is your dv. Okay? So we had x sine of x dx after the integral sign. If I let u equal x, then what's left over is dv, which is, in this case, sine of x dx. Okay? Now, if u is equal to x, then du equals dx. And if I said that dv equals sine of x dx, okay, that's supposed to be the differential of some function v. And one v that works is minus cos of x. If I take the differential of minus cos of x, I will get this dv equals sine of x dx. Okay? Now, I could have taken minus cos of x plus c, but I really just need one function for this to work, right? Okay, there's a question?
Sir, why is du equal to dx?
Oh, well, if u is equal to x, then du equals dx.
Like d is like a constant or some multiple or something.
And d is when I have if I have f of x, then df is the derivative of f times dx. Okay, by definition, that's the differential.
Okay, sir.
Okay. All right, so now I have all the pieces that I need for my integration by parts formula. Okay. So I is equal to uv minus integral v du. Let's fill in the pieces. U was x, v was minus cos of x, minus integral, v was minus cos of x, v du was dx. Okay, so we do a bit of simplification. We get the double minus signs to cancel each other out. And so that's equal to minus cos of x cos of x, plus integral cos of x dx. Okay, now I still have an integral to do, but now I've got an easier integral to do, right? Before I had x sine of x, I had to integrate that. Now I just have to integrate cos of x, but I know what the antiderivative of cos of x is. Okay, so that's minus x cos of x plus the antiderivative of cos of x is sine of x plus c. Okay, remember you had an indefinite, you started with an indefinite integral. You will have to have a plus c at the end. Okay. So is there any question for this one?
Yes, sir.
Yeah.
Sir, we can do it by we can do it without the substitution. We can do it without the substitution. Just apply by parts, and we get our desired result.
Yeah, I mean, it's up to you. You can use any valid technique that you like, but the more techniques you know, the more likely it is you'll find an answer, right?
Okay.
Okay, so right. I'm not, I'm not sure that you could find a substitution for this one. So then we use integration by parts. Okay. Now, as I said, the choice of u and therefore the choice of dv is up to you. Okay, so let's suppose we made another choice. Let's try this integral again, integral of x sine of x dx, but we are going to make another choice. We're not going to let u equal x this time. We're going to let u equal sine of x. Okay, if I let u equal sine of x, then what's left over is x dx. then x dx is dv, right? Because we're using integral u dv. Okay, so that's your u, that's your dv. If u is sine of x, then what's du?
Cos of x?
Cos of x dx. Cos of x.
Oh, yes. No.
We want the differential, so we'll have a dx at the end. So du will be cos of x dx, and if dv is x dx, then what's v? dv is the differential of v. What's v?
X.
1/2 x squared. Okay. Right? Because if v is equal to x squared over 2, then dv is x dx. All right. Now we have everything that we need for our integration by parts formula. Integral u dv is equal to uv minus integral of v du. Okay. So u times v was 1/2 x squared, minus the integral of v is 1/2 x squared, and du was cos of x dx. Okay? So now, this formula is perfectly true. There's nothing wrong with this, except that it doesn't help us. It's worse than what we started with. Before we had a monomial times sine of x. And now we have to integrate a binomial times cos of x. So we're not getting any closer to an answer if we make this choice. Okay? So here's the strategy. Supposing I have a polynomial times a sine or a cos. If you decide to do integration by parts, let u be the polynomial part. Okay? Why? Because then when you evaluate du, you get another polynomial, but the degree of the polynomial has been reduced by 1. Right? So before you had a polynomial, let's say of degree k, times a sine or a cos. You apply integration by parts. Now the next integral will have, in the integrand, a polynomial of degree k minus 1 times a sine or a cos. Right? So it's a simpler thing. The next integral that you have to do will be simpler. Okay? So next example. I is equal to integral of x e to the x dx. Okay? What will be your choice for u?
X.
You let u equal x, then du will be something easy. Du will just be dx, 1 times dx, right? And dv then is what? If u is equal to x, what's dv?
Ex dx.
Ex dx. And the integral, if dv is e to the x dx, then v is equal to?
Ex.
Exponential, right? Right. So let's expand on that strategy. If the integrand is a polynomial times a sine, a cosine, or an exponential, do the integration by parts with u being the polynomial part. Because then du lowers the degree of the polynomial by 1. Okay? All right, so I leave it for you to finish that one by yourself. It's a lot like the integral x sine of x or integral x cos of x. Integral x e to the x proceeds in much the same way. Let u be the polynomial part. Okay, another thing that you should see here. Example 3, I is equal to integral x squared sine of x dx. I'm going to let u equal what?
X squared.
X squared. I'm going to let u equal the polynomial part. Then automatically dv is equal to what?
Sin X dx.
Sine x dx. Okay. So with those choices, u equals x squared, dv equals sine of x dx. Then what's du? What's the differential of x squared?
2x dx.
2x dx. And if dv is sine of x dx, that's the differential of what function v?
Minus cos of x.
Minus cos of x. Excellent. So we get d equals twice x dx, v is equal to minus cos of x, and now we can apply integration by parts. Okay? So if I apply integration by parts, u is x squared times v minus cos of x minus integral of v minus cos of x times du twice x dx. Okay, so now let's simplify this. We'll cancel the double negative signs to get a positive. So we will get minus x squared cos of x plus twice the integral of x cos of x dx. Okay, so I had a polynomial of degree 2 times a sine. Now I've got a polynomial of degree 1 times a sine to deal with. So in this case, what I will do is I will apply integration by parts twice. I'll say I've got minus x squared cos of x plus twice some integral, let's call it I2, and I will evaluate that one by parts. Okay. So again, I've got x times cos of x. I'm going to let u equal x. I'm going to let dv be cos of x dx. If dv is cos of x dx, then v is sine of x. So x sine of x minus the integral of v sine of x times du. Well, if u is x, then du is dx. So this is x sine of x plus cos of x plus c. All right, so substitute that result for the second integral back into here. Right, so I replace I2 by x sine of x plus cos of x plus c. Now multiply through by the 2. I got minus x squared cos of x plus twice x sine of x plus twice cos of x plus 2c. 2c is just another constant. Twice a constant is a constant. I just call that one c prime, let's say. Okay. So if you've got a polynomial of whatever degree times a sine, a cosine, or an exponential, let u be the polynomial part. Then you'll get an integral where you've got a polynomial of degree. The degree is reduced by 1 times a sine, an x, or a cosine. And then you can just keep doing that. You can apply integration by parts over and over again until you get something that you know how to integrate. Okay, so you might have to apply integration by parts twice in some problems. Okay, so once again, you started with x squared times a sine, a cos, or an exponential. Integration by parts then gave you x times a sine, a cosine, or an exponential. And then another integration by parts, finish the problem. Okay. Are there any questions about that one? Okay. So let's not actually do this one. It would take a while. But tell me what the strategy is for this one.
So
You just
substitute-
integrate by parts again and again and again and again until you get x to the sine of x, I
Yeah,
believe.
and my
It
choice for
becomes-
you is what?
Huh?
X to the power 10.
X10.
X to the 10, the polynomial part. Okay? All right. Okay, so once again, you've got a polynomial times an exponential, a polynomial times a cosine, a polynomial times a sine. Always let u be the polynomial part. Okay, and then apply integration by parts as many times as is required. So that's guaranteed to eventually end, right? Okay. So how do you do this one? Integral x squared e to the 4x dx.
So we'll take u as x squared.
Right.
We'll solve.
Yeah. Okay. All right. What if I wanted to do a definite integral? So the integral from x equals a to x equals b of u dv, that's equal to uv integrated at a and at b minus the integral from x equals a to x equals b of v du. Okay. So let's do one example. Supposing I've got I is equal to the integral x equals 0 to x equals 1 of x squared e to the 3x dx. Okay, what's u? What's my choice for u?
X squared.
X squared. Then du is
e to
E3x
the 3
dx.
of
2x dx, right? What's dv?
e to the 3x.
E to the 3x dx. Right? dv is a differential, so it'll have a dx at the end. Okay, so e to the 3x dx, and then what's v?
E raised to the power 3 of x divided by 3.
That's right.
Since
Yeah.
that's just the integral of e to the 3 of x.
Yeah. Okay, so as you said, we're going to let u of x be x squared. dv is whatever's left of the integral. That's e to the 3x dx. du is twice x dx, right? The derivative of u times dx is the differential of u. And then v is 1 over 3 e to the 3x in order to get a dv of e to the 3x dx. Okay, so now we can apply our integration by parts formula. And as we do so, because it's a definite integral, we will also apply the values at the endpoints. Okay, so I is the integral of u times v, and then you have to evaluate it at 0 and at 1, minus the definite integral from 0 to 1 of v, which is 1/3 e to the 3x, times du, which is twice x dx.
Sir, I have a question.
Yes?
Alternatively, couldn't you just evaluate the definite integral first? Like, क्या कहते हैं, essentially पहले आप सारा ये evaluate कर लें, and then you just put the limits in the final expression you get. So once first you've evaluated x squared times 1 over 3 e to the 3x, you evaluate the integral, and then you put the limits over the entire expression which you obtain in the end. Is that still
Sure.
all right? Brilliant. Just wanted to clarify that.
Okay. So then if I apply the limits, that gives me 1/3 e cubed minus integral 0 to 1, 2/3 x e to the 3x dx. Now what do we do? Again, now you still have a polynomial times an exponential, but the degree of the polynomial has been reduced by 1. So we would apply integration by parts again. And right, so just keep applying integration by parts until you get an exponential by itself, and then evaluate the expression. Okay, this one's a little bit different. This is, let's say you have an exponential times a cosine, or an exponential times a sine. Then what should you do? Okay. Okay, so in this case, I is the integral of e to the x cos of x dx. I'm going to let u equal cos of x. So then what's left over is dv. and what's left over is e to the x dx. So dv is equal to e to the x dx. Now, if u is equal to cos of x, then what's du?
Minus sine of x.
Minus sine of x dx. Okay. And if dv is equal to e to the x dx, then v is equal to
E to the x.
E to the x.
Right. Right. So now we have all the pieces that we need to apply the integration by parts formula. Okay. So u cos of x times v e to the x minus integral v e to the x times du was minus sine of x dx. Okay, so that's equal to e to the x cos of x plus the integral sine of x e to the x dx. Now, when we had a polynomial times an exponential, we got a lower order polynomial for this the next time we had to evaluate an integral. So it looked as if we had made our lives easier. But here my life isn't any easier. I had an integral cosine times an exponential, and now I've got an integral of a sine times an exponential. And, well.
Sir, can't you just integrate by parts again? You could probably get the integral for e to the x times cosine of x again if you integrate the second integral by parts, right? And you know that I is basically the integral of e to the x times cosine of x, so you can set that as I. You put I as a variable, and then you can evaluate the integral. You'll get an expression in that way.
Right, exactly. Yeah, that's it exactly. Now remember, we let u be the cosine or the sine in this case, the first time we did the integration by parts. So the next time when you do the integration by parts, do the same again. Let u be the cosine or the sine. Okay? Okay, so then you will get e to the x cos of x plus, let the double integrals cancel each other out, integral sine of x e to the x dx. And now, once again, let u be the trigonometric function. Let u equal sine of x, and let dv be what's left over, e to the x dx. Okay, so now, how do we evaluate this? This is u, sine of x. What's du?
Cosine of x dx.
Cosine of x dx. And if dv is e to the x dx, then v is what?
E to
Simply
the
e
power
to the x.
E to the x. Okay? So u sine of x times v e to the x minus the integral of v e to the x times du, which is cos of x dx. Now, it kind of looks like I'm going in circles, but actually my life is better now because I've recovered the original integral. I've got I is equal to e to the x cos of x plus sine of x e to the x minus the original integral, which I was calling I. So I can bring this I on the right-hand side over to the left-hand side where the other I is. So I get twice I equals 1/2 cos of x plus e to the x sine of x. So I is equal to 1/2 e to the x cos of x plus e to the x sine of x.
And there'll be a 1/2.
Yeah, I'm missing a 1/2, right. I should fix that. 1/2 e to the x sine of x. And this was an indefinite integral, so it should always end with a plus c. Okay. All right. Any questions on this one?
Nope.
Okay. All right. So once again, so what should our strategy be? If we have an integrals of the type cos of x e to the mx or sine of kx e to the mx, What is the strategy?
So we'll have u as cos of kx or sine of kx.
Yeah, that's right. And you do that twice to recover the original integral. Okay, so you should, as a test for yourself, you should do this one. I is equal to an integral sine of 3x exponential of twice x dx, and see what you get. And you can plug that into Wolfram alpha and see if you got the right answer. Okay. Any questions before we go on?
No.
Okay, so the next thing is, here's an integral that we haven't been able to do before. I mean, maybe there is some way, but I can't think of another technique that works for this one. So I want to know what the integral of log of x dx is. Okay, so let's say we want to, I can't think of a substitution that works. So the other choice is, the other choice would be, let's try integration by parts. Okay. So what are my choices here?
1 into log.
You can set log of x as your v, the term you need to differentiate, and you can set dx as your dv, the expression you just need to integrate.
Okay.
So it becomes x times the natural log of x minus 1 over x times x. So it just becomes the natural log of x minus x times the natural log of x minus the natural log of x.
Yeah. Okay. So I'll make the choice u equals log of x, right? And then dv is whatever's left over. The only thing left over is dx. So that means dv equals dx. Well, if u is equal to log of x, then dx is 1 over x dx. And if dv was equal to dx, then v is equal to x. Now apply the integration by parts formula. That's u is log of x times v, which is x, minus the integral of v, which is x, times 1 over x dx. Okay? So that gives me x log of x minus the integral of 1 dx. X and 1 over x cancel. The only reason they wouldn't cancel it would be if x was equal to 0, in which case log of x never made any sense in the first place, right? So this is the integral of x log of x minus the integral of dx, 1 dx, okay? So that's x log of x minus x plus a constant, okay? So now we know how to integrate the logarithm function. The integral of logarithm is x log of x minus x plus c, okay?
Can you repeat this again?
You want to see that again?
Yes, sir.
Okay, so I've got integral log of x dx. If I want to do this by parts, I have to assign some part as u and some part as dv, right? Well, there isn't much of a choice for u. I have to pick some function, and there's only one function sitting in there, right? So I let u equal the logarithm of x. Then what's left over is dv. So what's left over here is dx. So dv equals dx. Now the differential of log of x is 1 over x dx. And the integral of 1 is x. So v is equal to x. Okay. So I picked u. That forced the choice of dv. Then I figured out du and v. Now I can apply my integration by parts formula. So integral I is equal to uv, log of x times x, minus integral of v, which is x, times du which is 1 over x dx. The x and the 1 over x cancel. So this is x log of x minus the integral 1 over x dx. The antiderivative of 1 is x. So that's x log of x minus x plus an arbitrary constant c.
Got it, sir. Thank you.
Okay. All right. Let's do this one. I is equal to the integral of x log of x dx. How am I going to make my choices?
You said u is equal to x.
So we take u equals to log of x.
Yeah, okay, so that's right. So sometimes both possible choices will work, right? But let's take this choice. U equals logarithm of x. dv is what's left over. So if I've used log of x for u, what's left over is x dx. That gives me du is equal to differential of log is 1 over x dx. And if dv was x dx, then v is equal to x squared over 2. Okay? So then I is equal to uv log of x times x squared over 2 minus integral of v x squared over 2 times d, which is 1 over x dx. So that's 1/2 x squared log of x minus 1/2, I'll pull the 1/2 outside of the integral sign, and x squared divided by x gives me x dx. Now the antiderivative of x is 1/2 x squared. So now I have 1/2 x squared log of x minus 1/4 x squared plus c. Okay. So, any questions about that one?
Sir?
Yeah.
Sir, we can let u is equal to x as well.
Yeah, and like I said, it might be useful as an exercise to make the choice with u equal x and see what you get. Remember, now you know how to integrate log by itself, right? It's x log of x. Yeah, let's see, right? So, okay. Well, what if I had higher powers of logarithm? Sorry, higher powers of x. So I had integral x to the m log of x dx. M can't be equal to -1. Well, you should try it with m equal to -1 and see what would happen. Again, let u equal log of x. And as an exercise, you should evaluate this.
Sir.
Yes?
Sir, in this example, can you put u is equal to x power m, or we can only do u is equal to log of x?
Okay, so you should try letting u equal x to the m also, and see what you get. I think you can, and for these ones, I think you can actually do both. Right? Okay. All right. Are there any questions about this?
Sir, but using x to the power m as u wouldn't be a good idea, right? Because
Well,
logs
okay.
Logs are the most it's the most hard to integrate them, and the first option of u should always be log, and then algebraic expressions.
Okay. Well, I mean, why don't you try it both ways and see, and you know, you can decide for yourself which one would be more difficult. But I think you can actually do it with both in this case.
Okay.
I think Basit had a question.
Yes, sir.
Yes.
Sir, can you move back to the slide where we had I in the integration part, and we took that to the other side and made it 2i.
Oh, sure. Right. That was this one, right. So if you have an exponential times a cosine or an exponential times a sine, this sort of thing will happen. Yeah.
Sir, I get that whole concept. What I didn't get was why did we add a constant c? Because when we when we got e, we took that to another side. So why did we add c in there? And I just don't get that.
Okay, so I think, yeah, I think the thing is that when you had this and you got your I again, technically you didn't get exactly I again. I plus C would also work here.
So, sir. So sir, didn't we get the extra c from the integration we did of cos of x initially from the by part from the first by part?
Yeah, that might be another way of looking at it.
All right. Thank you, sir.
Okay. All right. Are there any more questions before we go on to the next part? Yeah.
Sir, could you please explain how this rule was derived just one more time?
Yeah.
Using that product rule.
Yeah. Okay. So we start with the product rule. We say the product uv, the derivative of u times v is u times the derivative of v plus the derivative of u times v. Now, if I want to isolate u times the derivative of v, then I would get that u times the derivative of v is the derivative of u times v minus v times the derivative of u. Now I want to integrate, I'll slap an integration around it. Then the integral of u v prime dx is equal to integral of u v prime dx minus the integral of v u prime dx. But v prime dx is by definition the differential dv. And u prime dx is by definition the differential du. And the integral of the derivative of uv is by definition, well, it's uv plus some c, basically. Right?
Okay, got it, sir. Thank you.
All right. Any other questions before we do trigonometric substitution? Okay. All right. So the last topic of the course is trigonometric substitution. Okay. So
this means no class on Thursday.
now there'll be a class on Thursday because we're not going to be able to get through all of this. Or
Okay, sir.
even if you get through all of this, you'll need more practice. Trig substitution is so there's a hierarchy, right? Can I do this integration directly? No. Can I do it with the substitution? No. Then you try integration by parts. And then if you're unfortunate, then maybe you try trig substitution. Okay. So trig substitution actually stands for a whole bunch of substitutions, which depend upon the trig identities that we have seen before. Okay. So as I said, trig substitution should be the last thing that you try. Okay. Okay. So let's look at one that doesn't require trig substitution. Okay. So I've got integral of x root of 1 minus x squared dx. Okay. I don't know how to do it directly, maybe, but I can see a substitution. I can let u equal 1 minus x squared, and then I can see that I've got a constant times the differential twice x dx for the rest of the integral. So the substitution u equals 1 minus x squared suggests itself, and then you would be able to do the integral. Okay. Now let's see a slightly different one. Let's say I have root of 1 minus x squared. Okay. So if my instinct is to say let u equal 1 minus x squared, but then I don't see a constant times minus 2x dx in the rest of the integral. So u equals 1 minus x squared will not work here. Okay? But let's say we're stuck trying to do it, right? Let's say we still have to do it. Just because we can't do it with the techniques that we're familiar with doesn't mean, all right? So we learn another technique to do this. Okay? Okay. So if you recall, so these techniques are based off of the trig identities and the derivatives of the trig and the inverse trig functions that you've seen before. So one of the famous trig identities is cos squared theta plus sine squared theta is equal to 1. And that means that cos of theta is plus or minus the root of 1 minus sine theta, sine squared theta. And for the, if we're allowed to pick theta, then for the right values of theta, cos of theta is equal to the positive root of 1 minus sine squared theta. Okay? So when I see root of 1 minus x squared, that puts me in mind of this, that root of 1 minus sine squared theta is equal to cos theta, right? Okay. So here the substitution would be x is equal to sine of theta. Okay? Now remember, if you're making a substitution and you're saying that x is going to be some function of theta, then your dx is also going to involve theta. Right? You don't want to, when you do your substitution, you don't want to leave any x's in the problem. Right? Everything then should be in terms of theta. Okay. So I is equal to the integral of root 1 minus x squared dx. I replace x by sine theta. So this is the root of 1 minus sine squared theta. And what's dx?
Cos theta d theta.
Dx is cos squared theta, cos theta d theta. Okay? So the integral of root of 1 minus x squared is replaced by cos theta, and dx is replaced by cos theta d theta when you make the substitution that x is equal to sine theta. Okay? Now, this is the integral of cos squared theta d theta. Okay? Now remember your double angle formulas? What was cos 2 theta?
Cos squared minus sine squared theta.
Yeah, cos 2 theta, just in terms of cos theta and sine theta, is cos squared theta minus sine squared theta. And then you can manipulate that to get that cos squared theta is the same as 1/2 cos of 2 theta plus 1/2. Okay? So I replace cos squared theta now by 1/2 cos of 2 theta plus 1/2. Yes, Basit has a question?
Yes, sir, but doesn't the the double angle identity, can we put the other formula, would it work or not? So, or we only
Yeah,
have
I
to
mean,
put it
the idea is to get something that you can integrate. So if you want to replace cos squared theta by something else that you know how to integrate, do that also. That's fine. Okay, but I chose this one. So I replace cos squared theta by 1/2 cos of 2 theta plus 1/2. Okay. Now, integral of cos 2 theta is 1/2 sine of 2 theta, right? So this is 1/4 sine of 2 theta plus the integral of 1/2 with respect to theta is theta plus a constant. So is this okay so far?
Yes, sir.
Okay. Now I'm kind of done, but I'm not quite done because this theta and this substitution is something that I put in myself, but I was asked for something in terms of x. The original problem had x's and dx's in it, right? Not thetas. So I have to replace all these functions of theta with functions of x. Okay, so I have 1/4, and then I'm going to replace sine 2 theta by twice sine theta cos theta. Okay, so that would give me 2/4 sine theta cos theta plus 1/2 theta plus c. Okay, I just did that to make my life easier. Okay, now what was sine theta? I let x equal sine theta, right? And what was cos theta? Well, I calculated that. I said cos theta is root of 1 minus x squared, right? So sine theta is x. Cos theta is root of 1 minus x squared. 1/2. Well, what was theta? If x was equal to sine theta, then theta was equal to the inverse sine of x, right? So now I replace everything. I get rid of the thetas and I get rid of these functions of theta and I replace them by functions of x. So that's 1/2. X replaces sine theta. Root of 1 minus x squared replaces cos theta. And inverse sine of x replaces theta. And we get the final answer.
Sir, can you please explain this from the previous step? I could not understand it from there.
Okay, so I had
Yes, sir,
1
this
quarter
one.
from here.
Sir, above this one, you have 1/2 cos 2 theta.
Yeah.
Yes, sir. How did you? Yeah. How did you, sir, write that thing into this thing? Yeah. From
Oh,
here.
okay. So cos of 2 theta is cos squared theta minus sine squared theta, right?
Yes, sir. Yes, sir.
Right? So I use that identity, and I also play around. Sine squared theta is also 1 minus cos squared theta. Right?
Yes, sir.
So I play around with that, and I'll get that cos squared theta is 1/2 cos of 2 theta plus 1/2.
Okay, sir.
All right, any other questions?
Sir, then what about the next step, sir? What about the next and till how do we convert it into x?
Okay, so sine of 2 theta is twice sine theta cos theta. So 1/4 sine of 2 theta is the same as 1/4 times twice sine theta cos theta. So that's 2/4 sine of theta cos of theta plus 1/2 theta I leave alone and plus c I leave alone. Okay? Now, how can I replace x? Well, way back when I said let x equal sine of theta. So that replaces my x. And I already found that root of 1 minus x squared was cos theta. So that I replace sine theta by x. I replace cos theta by root of 1 minus x squared plus 1/2. Now, if x was equal to sine theta, then theta was equal to the inverse sine of x. So I can replace theta by the inverse sine of x, and that gives me my final answer.
Okay, sir. Thank you, sir. I got it.
Okay. All right. As an exercise, you could try replacing this by x is equal to cos of theta and see what you get. When the result may look different than the previous result, but remember there's a plus c in there, so they will only differ by a constant. Okay. All right. Now let's try generalizing this. Supposing I have I is equal to the root of a squared minus x squared dx. Right? I know how to handle root of 1 minus x squared dx. How could I handle root of a squared minus x squared dx? How could I make it look like something I already know how to do?
So we will take x is equal to a cos and theta या फिर a sin theta.
Right. I can let x equal a sine theta, for example. I think x equals a cos theta would also work. And then I have, underneath the root sign, I've got a squared minus a squared sine squared theta. So I factor out the a squared. So I've got a squared times 1 minus sine squared. So a squared cos squared theta, right? Okay. So, and then the integral proceeds much like the same that you had before, except you've got a's, some constant a floating around. Okay. So if you have integral root of a squared minus x squared dx, you can try x equals a sine theta. If you've got root of a squared minus x squared, and you've also got something else involving x in the problem, look for a substitution first. And if all else fails, right, trying all the other techniques, if it doesn't work, then try x equals a sine theta. Okay. Okay. Let's take a look at this one. I is equal to the integral of 1 over the root of x squared minus a squared dx. What do you think might work? Okay. I think somebody had an answer, but you need to yell louder. Okay.
Is it secant?
Yeah, that's right. That's right. So remember that 1 plus tangent squared theta equals secant squared theta? So then secant squared theta minus 1 is tangent squared theta. So then a squared secant squared theta minus a squared is equal to a squared tangent squared theta. Okay? So then we look back here. That suggests that we let x equal a secant theta. Okay? So if you've got a root of x squared minus a squared, and you're absolutely forced to do trigonometric substitution, the substitution that you want to try is x is equal to a secant theta. Okay? So if x is equal to a secant theta, remember the derivative of secant theta is secant theta tangent theta, right? So dx is equal to a secant theta tangent theta d theta. And then root of x squared minus a squared is equal to a tangent theta. So then we've got 1 over the root was a tangent theta times dx was a secant theta tangent theta d theta. Now we're fortunate the tangent thetas canceled each other out, right? And the a's even cancel each other out. So I've got integral of secant theta d theta. Okay. Now, right, this was one of those ones that we said, these were these new results that we had now that we had the logarithm and the exponential functions, right? Integral of secant theta d theta is logarithm of secant theta plus, logarithm of the absolute value of secant theta plus tangent theta plus c. Remember, this is an indefinite integral, so always a plus c. Now, how do I replace secant theta? Well, x was equal to a secant theta, so x over a is secant theta. And we had that a tangent theta was root of x squared minus a squared, so tangent theta is equal to 1 over a times root of x squared minus a squared plus c. So now, if I do my substitutions, I get logarithm of the absolute value of x over a plus root of x squared minus a squared over a plus c. And that's absolutely fine as a result. But if you want to play around with properties of logarithms, you're dividing by, there's a division in there, right? So when you have a division and you take the logarithm, you end up with log of the numerator minus the log of the denominator, right? And you're dividing by a here. This is log absolute x plus root of x squared minus a squared minus logarithm of a plus c. And logarithm of a is a constant plus another constant, so you can combine it as another constant. But as I said, the first result is perfectly fine as an answer. You don't have to go doing these other gymnastics. Okay. Are there any questions about this? Okay. All right. What if I had integral of 1 over a squared plus x squared dx? What does 1 over a squared plus x squared remind you of?
So the derivative of tan inverse.
Yeah, that's right. Right? Remember, the derivative of the arctangent of x is 1 over 1 plus x squared. So if you try taking the derivative of inverse tangent of x over a, you will get something like what you have there, except you're off by a little bit by a constant. Okay, so you can, so for something of this form, you can try a substitution of the form x is equal to a tangent theta. Okay, so I think that's enough for today. We can try, hopefully we'll finish off the trig substitution discussion in the next class. Okay, so are there any questions? Yeah, Basit has a question.
Yes, sir. Sir, can you move to the question where you did 1 over under root x square minus a square?
1 over this one?
Yes, sir. Sir, can you move to the next slide? I just want to see which identity will be.
Yeah.
Okay, sir.
Okay. All right. I will see you all on Thursday.